Hi guys, today we will talk about the logic gate inverter in microelectronics, which has a lot of useful application. So we will go also into a bit of layout, propagation delays, and of course SPICE simulation. Let's do this. So this is an inverter. This is not the power inverter which transforms the DC to AC used for brushless motor. No, this is the logic gate inverter. And the scope is to invert the signal from 0 to 1 and 1 to 0. So it is formed by a PMOS here and an NMOS here. The NMOS is connected basically always to ground, and the PMOS is always connected to VDD, so that the source is higher than the gate and the source here is lower than the gate. Of course, it depends on the input signal, but the scope is that if you have 1 here, this is on, and so you have 0, because you have the path to ground. And if you have 0 here, then the PMOS is on, and you have VDD. Simple as that. The problem here is that you have to... the problem here is with the layout. And now I will show you another slide, another set of slides, which is this. So basically in the VLSI, when you have to design this logic gate here, you don't do with just a discrete MOSFET, but you do with an entirely different layout process. So here's the thing. You indicate the MOS with a ratio between width over length. If you don't remember who are these, let me remind you just briefly that a MOSFET, this is the section of the MOSFET. You have the N+, let me use another color. This is by the way, the saturation region. You have basically a channel like this. Let me draw minus. This is the saturation region, and this is the length, the effective length of the channel. This is the depletion region, that L, and this is called the pitch off point. Now, here you have the dielectric, which is basically made in silicon dioxide. You have to remember that the constant here is 3.9. This will be very important because when we will study the parameters, this y of this epsilon of r will be important. So basically, and of course the rest is made of P. So this is basically how a MOSFET is made. If we come back here, this is a stick out diagram, and the ratio here is indicated. Oh, sorry, I forgot that after the oxide there is the polysilicon, and this is the gate. Sorry, I forgot that this is the source, and this is of course the drain. Here we have also the body, and in power MOSFET the body source are short-circuited, but here you need the body as well. But anyway, these are indicated with a ratio between the width over length. The PMOS are always bigger than MOS, basically because the mobility of the PMOS, because the mobility UP of the PMOS influence the dimension of the PMOS itself. And here this diagram on the left is called sticky diagram, and it is an approximation of the diagram on the right. So basically, you have if you studied technical drawing, you know that this is metal, this is another kind of metal, this is the diffusion, and this is the polysilicon. So basically, here you have the VDD, the power supply, and here you have the ground. Imagine that this is an inverter. And it is more intuitive to look at that rather than this. So all of this is metal. The power supply and the ground are metal. Then the input port is polysilicon. And then, of course, also the power output is metal. This is the contact, which basically are a via. The via is a connection between, if this is the layer 1, and if this is the layer 2, the via connects the two layers like this. And they are called vias, metal vias. You will see a lot of this diagram on the net and how to construct them, and then they are indicated by the ratio lambda. 6 lambda, 2 lambda as the distance, and so on. But this is a very, very specific part of the electronics, and I don't think that I will ever make an inverter from scratch, because this is an extremely specific part of electronics. So let's skip to the characteristic of the inverter. So this is the characteristic of the inverter and how the MOSFET are working in each of these regions. This is the first thing that we will see in LTSPICE just by looking at the output and the input in a DC characteristic sweep. So this point here is exactly at VDD over 2, and the gain here is very high, meaning that if you put one inverter after another, you are actually improving the converter, improving the gain. This property is called regenerative property. Let me write this here. Regenerative property. So if you put inverters in cascade like this, you're gonna improve the response time, as you can see from this graph here. So this is V0. This is the first scene. This is the first pulse here, V0. Then the inverter inverts it, and you have V1, which is like this. Then at V2, you have basically a buffer stage. So the input, so V2, V0 should be equal to V2. But as you can see here, you have a better improvement, a better rise time than V1, but in comparison with V2, you have a bit of delay. In fact, the next topic that we'll talk about is the delay propagation from the input to the output. As you can see, there is a bit of delay. This is the input pulse, and this is the output pulse of the inverter. There are delay called TPDF, TPDR, TF, and TR. So TPDF is basically the propagation delay in the fall time of the output, and it is taken from half the voltage to the same amount here at half of the output. This is called TPF. The same for TPDR. It is basically from the output, from the rise of the output time. To understand why there are this kind of delay, you can use basically the switching, the approximation of the switch, like an RC model. If you use this model here, you have to remember that PMOS is bigger, and so you will have the ratio between UN over Pn times R, and for instance it can be equal to 2. So this is a NMOS, okay? Each of these MOSFET have a lot of capacitance. CGS, all the capacitance between the body, the drain, you already know the story. Just draw a capacitance between each of these terminals, and you have the joypad. So, and you substitute the resistor here, and you do the same for so this is for the NMOS, and this is for the PMOS. And now let's switch to LTSPICE, and we'll see in order First, the characteristics of this, the ideal characteristics. This is the first thing that we will see. Second, the regenerative property. We will try to build a buffer and compare it to LTSPICE. And then third, we will see the propagation delay. This will require actually a little bit of time, but I hope that you can follow me. So let's open LTSPICE. Now, the first thing that I wanted to tell you is that you don't have to select this MOSFET here. It won't work because the body is short circuit with the drain, with the source in the NMOS. You don't want to do that, so leave the drain open for now. The same for the PMOS. PMOS 4 is the choice. Then we will short circuit. Then we will make a short circuit. Now, LTSPICE is quite intelligent because he knows that if you're selecting this kind of MOSFET, he knows that you want to use the model of the real MOSFET. The length, the width, the drain area, the source, the how many parallel devices you need, and etc. So we will first do an analysis with the ideal MOSFET and the PMOS. Let's first short circuit the body with this, and also for the PMOS. Let's use the voltage VDD, 5 volts. A little bit of trick. Propagation delay depends on VDD. The higher, the better. So basically, 1 volt is not suggested. 3.3 is better. Ah! It's too big. Okay. Okay, so let's connect it like this. And now let's use a pulse .param d equal to 0.5. Well, since we are in the digital domain, we can even say that the switching frequency of this is 1 GHz. And we could not be so wrong about it, because it is a speed which can really happen. And this is V in, and so this is our pulse between 0 and 5 volts. The delay, nothing. Rise time 1 nano. We will make it fast, and T on D over Fs, like we do in power electronics. 1 over Fs. I don't want to show you this because you already know what it is. Ah! Okay. Let me just draw this. And that's it. Now, on the other hand, we wanted to take also this input voltage and feed it to an inverter made with LTSPICE. We will call this guy... let me take this... here, because I want to make an extension of this. Let me do this, and this is a buffer, so that we can make an easy comparison between the input and the output. This will be out 1, and let's connect also the input voltage to a double series of buffer. Remember that you have to select here on the value V high equal to 5. Okay. Otherwise, you will have 0 and 1. And this is out 2. Okay. So now this is a battle between me and LTSPICE. Who will win? Well, of course, LTSPICE wins. But why? Let's run the simulation for, I don't know, 10 nano. Should be enough. I wrote it wrong. V high equal to 5. Let me run the simulation. Let me put like this because we have enough space. So this is the, whoa, 1 nano is too low. We need to do 1 femto. This would be extremely, okay, so just put 5 nano. 4 nano is enough. And this is the output voltage. As you can see here, you have a very steep output voltage because this is an ideal buffer, what I made. If we make a comparison, you can see that the output voltage 1 actually is improving the input voltage. As I explained it to you, there is the regenerative property. So if we select this output here, and if we put a minus and we add minus and we add 5, so we are first inverting the first output like this. Then we will move it up like this. You can immediately see the difference between this output here and the second output. This is the regenerative property. The gain is improving your signal. So a buffer made with 2 inverters is actually a very, very good and very, very fast, stable buffer. Also, it would seem the problem here that between 2 of these buffer there is a line, there is metal contact, and this implies propagation delay, and so this is the real result. To get a more accurate result, well, first of all, let's check also the output voltage 2, and of course it wins. And of course it wins. So the output voltage 2 wins over your handmade inverter. Well, this was to be expected, of course. But above all, you want to check the characteristic of this. Just do .dc, and the first source to sweep is Vin. Type of sweep, of course, linear, between 0 and 5 volts. Increment as you wish. You do run the simulation, and you will see the output voltage 1, the Vin, and if you take the power supply VDD, let me call it here VDD, let me run again, VDD, output voltage, and Vin, and you divide VDD over 2, yes, gotcha. You will see that this is the point of the threshold of the circuit. Okay, so there is a little bit of discrepancy, but I don't care. So this is the threshold point of your inverter. Now, this is too good to be true. Almost too good to be true. The real problem is the propagation delay. So, the first thing that we want to do is to import the real model of the MOSFET. So, first of all, let me save it. Logic gate inverter. And so, second, you want to characterize the MOSFET by basically the most 4 important parameters, which basically are L, W, VTO, and KP. What is KP? Well, if you don't remember, KP is basically the constant related to the oxide capacitance of the MOSFET. And KP is must be declared on LTSPICE, and it has different values based on PMOS and MOS. And if you really want to know the formula, KP is equal to mu times Cox. And now Cox is the oxide capacitance. You can even make the calculation of Cox if you want, and but it is a capacitance which you can find in a common datasheet, so I think that there is no need. For LTSPICE, the value, this value here in LTSPICE is from it should be around 20 micro, and the unit here is A over B square. The VTO, it is the zero bias threshold voltage, and the default value is 0, which is not true in reality. So now that you know, we can use the statement dot model NMOS 1 NMOS. So we will put reasonable values. These are always in the order of the micro, but if you wanted to do reasonable values by yourself, you have to take into account the following. The PMOS is bigger than NMOS. This is important. So it is reasonable to say that the V is equal to 8, L is equal to 2, 8 micro, L is equal to 2 micro, VTO is equal to, I don't know, 0.5, 1, Kp is equal to 50. For the PMOS, the width of the channel must be double, at least, double or bigger than the MOS. So we will put 60 micro. And I don't know why I put all these commas here. I don't think that you need commas. L is equal to 2U. VTO is equal to 0.5. Well, actually here it is minus because it is a PMOS. And the Kp equal to 25. Now let's run the simulation again, because we put we put now a real NMOS and real PMOS in the circuit. Let's run the simulation again, and okay, the characteristic has not changed at all. Let's check instead. The transient as we did before. Let's see if we can appreciate a change. No, it is still good. So you do remember how it was before? It wasn't like that. Now there is a big difference between out 1 and out 2. Yes, there is. So we can make a screenshot of this. So let's capture this, and let's put it here. Oh, my bad. And let's cancel this, comment all this, let's run again. Well, there is indeed a big difference. So before here, we had the output voltage, which is improving a bit, but not so much. But now there is a really big improvement in the ideal case. And it's very near to the actual inverter gate. But since we want to study the propagation delay, I think that we have to take into account of the VTO here also. And so we can't neglect this factor here. Now that I have increased the threshold voltage, it has even worsened a bit. Because here I have 0 before 1 volt, so let me put 0.1. It is an unrealistic, but so now it has improved a bit. So what we want to do now is to use this model here. The model here can be also represented with a load capacitance. So basically, you are saying that what your inverter sees, you have your inverter here with a load capacitance, CF. So we will add the load capacitance here. This is called C load, and this is called 1 pico, even 1 femto, because even 1 pico here can be significant, very, very significant. You see now that there is a very big attenuation. I should also put the capacitance here, if you really wanted to do the simulation right. But if you want to find all this time here, you can find all this time here in 2 possible ways. You can either select the cursor here, but before you can do that for each in each time in each simulation, you will probably get old, because let's say that I want to change some parameters. I have to select the cursor each time. It can become very, very, very tedious if you think. So I don't think that this is the appropriate way to do it. But what you can do instead, is to use the statement find when. So suggestion: use find when statement. The find when statement, it basically calculates the time that you need. Okay, the time that you need when some condition happens. Let me write it for you. You write like this: .meas t1, for instance, find time. So find what? Here you have to indicate the variable, and the variable time is here. Find time when, now you have to indicate a voltage, so V of in. I didn't put the label in, but I will put it now. It is equal to 2.5. This is the time when we are half of the input voltage. And rise equal to 1. And .meas t1, t2, find time when V of out 1 is equal to 2.5, fall equal to 1. And of course now we can take the. So what we are going to do now is to calculate. First, you can find when the input is at this point here, and we write it here. When the in is equal to 2.5 and rise equal to 1, and it is here. Then we have to find the point in which the output is to 0.5 on the default time in an inverter. Yes. I am in fact stupid because this works with an inverter. So the propagation delay will be extremely high. I will cancel this and will make an inverter in a moment. So now dot measurement time propagation delay TP let it call PDF the difference between time 2 and time 1. So let me cancel this. Let me cancel all of this. Let me connect it to here. And okay, now we should be fine. Let me run the simulation. This is the in. Okay, V of in. Let's run the simulation. This is the input voltage, and this is the output. This is the output voltage, and this is the input voltage. If you see the error log view, error log, you can see that it has found the time in which effectively we have 2.5. He says that we are at 5, basically at the beginning of the. Okay. Let's check the error log again. Where are ya? Where is the error log? I couldn't find the error log because I was on the graph. So it says that we have 1.37 as propagation delay. Femtofarad. 1.37 femtosecond as propagation delay. Well, from the graph here, I can say that he is probably right, because he's taking this time here, and he's taking this time here, and he's making the difference between this time here, which is 2.1, and this time here, which is more or less 0.5. So I would guess that the difference is around 1.6, 1.7, and it says 1.37. So yes, I think that is right. Okay, this is working. It's calculating the delay. Okay, this is fine. So you even know now how to calculate the delay of your thing. We can increase also this guy here to 10 pico, and you will say that of course the propagation time will increase. Let's check the difference. You now have from 1.37 femtosecond, you now have 12 femtosecond. It's reasonable. You see, this delay is more consistent. If we do the same instead with the out 2, point at out 2. No, come back here. vout2 pdf2. We make another parameter called pdf2. We can less than 2 connection to out2. Let me see the error log. So I probably have to comment this. So as you can see, the propagation delay, of course, of an inverter, of an LTSPICE inverter, is way less than your handmade inverter. Well, I think that I can close the lesson here. Thank you guys for following me. I had to study a little bit of microelectronics to do this video. Hope that you like this video, and see you in the next one. Thank you guys.